Ruiwen, please go ahead. Oh no,
Computer scientist,
the image is flipped.
so I use slides. So let's start with a computer science problem. It's a old decidability problem. Actually, one of the first problems that's shown to be undecidable after the halting problem. The input is you're given an input, it's a set of square matrices S and a target matrix T, and you want a program that decide whether there is or not a sequence in S, possibly with duplicates, such that the product is equal to the target matrix T. And of course, you can't invert the matrix E. And stated more formally, that's just the sub-group membership problem, meaning we work in a fixed group G, matrix group in this case. You're given the element T in G and the subset S, finite subset S of G, and you want to decide whether T is in the sub-semigroup generated by S. Markov proved this to be undecidable for 6x6 matrices. And very similarly, there's this classic group membership problem. So also, we work in a fixed group G. You're given the element T in the group G and the subset S of G. You want to decide whether T is in the subgroup generated by S. And the classic result that these problems, or especially the group membership problem, is undecidable if we work in the direct product of two free groups, the classic construction. On the other hand, if we work in a single free group, then the semi-group membership is decidable. Well, because the group is a semi-group, then the group membership is also decidable. And also here in this case, since the group is semi-group, the semi-group membership is also undecidable in the direct product of two free.
So a stupid question, like there's obviously like the set could be finite, it could be, for example, enumerable or decidable. Like
we only consider finite.
okay, yeah. Okay.
Otherwise, it can be much more challenging.
Okay.
So yeah, so we said, well, if the group G contains a free group or a direct product of two free groups, then it's hopeless. So another extremity, since we mostly care about matrix group, is solvable groups. So by this alternative. And in fact, group membership has been proven to be decidable in many classes of solvable groups. For example, nilpotent groups. Well, sure, we're mostly considering finitely generated groups. It's decidable in polycyclic groups. It's decidable in metabelian groups. So it's natural to ask, oh, what about the semi-group membership? Can we decide that? Unfortunately, no. So there exists a two-step nilpotent group, finitely generated, where semi-group membership is undecidable. So no hope of solving in metabelian groups, polycyclic groups, or nilpotent groups. The idea here is to encode the Hilbert's tank problem, so deciding whether a polynomial has integer 0. So maybe semi-group membership is not the good question to ask. Then the idea is to ask easier problems, and some of the problems we would like to consider is identity problem, inverse problem, group problem. So they can be seen as the special cases of semi-group membership where you have the problem of not including inverses. So the identity problem is to ask whether the semi-group generated by the set S contains the neutral element, the identity element.
I am only interested in invertible matrices. I know there is a mortality problem.
In this case, yes. More generally, no. That's all.
Well, there are no matrices here, but there's an ambient group.
Yeah, so
the ambient group will have invertible matrices, yes.
So there's no problem. But in general, yeah, I'm really interested in semi-group membership in matrix semi-groups instead of groups as well. But that's not a part of this. We have inverse problem, whether the inverse of A1 is in the semi-group generated by S, so the A1 can be inverted in group, and finally a group problem whether the semigroup is actually a group. So there are other interpretations of these problems. For example, when we're given a finite set S in the ambient group G, let S star denote the 7 words over the alphabet. Then there's a natural map from S star to G called multiplication. And essentially identity problem asks whether you can find a non-empty words whose product is the identity. It has also a nicer geometric interpretation. Is you ask whether the Cayley graph associated to the set S contains a directed cycle. Similarly, the group problem is if you can formulate it in a similar way. Is there a word in over the alphabet S using every letter of S such that the product is the identity? Because if that's the case, then you can invert every letter in the alphabet S. And if every letter in the alphabet S is invertible in the semigroup, you can multiply them together and get a word that's the identity. And it's equivalent to asking whether the Cayley graph associated to the generators S contains a cycle where every label is used. So let's start with the easiest cases. So what's the group problem in a abelian group? Z to the power n. So we're given a set of vectors, integer vectors, and the semigroup is a group if and only if the cone generated by these vectors is a lattice. And that essentially says you can find positive integers n1, n2, and k such that this linear combination of vectors is equal to the trivial vector. So that's just solving a system of linear equations over positive integers. And you can do that using integer programming or even linear programming because the equation is homogeneous. That's obviously decidable. So yeah, that's what I said. And interestingly, you can even generalize that to nilpotent groups. So it's a recent result that for k at most 10, let G be a k-set nilpotent group and S be a subset of G, finite subset, which generates G. It's not a big assumption because you can always restrict it to a subgroup. Then the semigroup generated by S is a group if and only if it is a group in the abelianization of G. So for nilpotent groups of class at most 10, you can reduce it to the abelian case. My guess is you can, well, it's not limited to 10, because, but the proof relies on a lot of assistance from computer algebra system, and somehow after 10, it's really hard to run the program. So let's say it works up to 10, but probably to 20 or 30. And but we're not interested in nilpotent groups. We're interested in metabelian groups. So we call that the group is metabelian if its commutator is abelian. And also there's a problem of how to represent a metabelian group. We choose here using a classic theorem of Magnus extended by Bonstar. A metabelian group can, well, a finitely generated metabelian group can always be written as a semi-direct product of Y and A, where A is a finitely generated abelian group, and Y is a finitely presented Z of A module. And everything is effective. There's no problem inside. So, for example, given a finite presentation in the class of metabelian groups, you can compute such a semi-direct product using this from this finite presentation. So we show that group problem in metabelian groups, so let's say semi-group problems in metabelian groups, is equivalent to solving linear equations over positive integers. And interestingly, what we will show here is that the group problem, so whether a semigroup is a group, is in metabelian groups is related to solving a system of linear equations over this semi-ring. So it's a semi-ring of polynomials with only positive coefficients. And this is much more difficult because a priori we don't get a bound. So say if we have a system of linear equations whose coefficients are just polynomials, it's really difficult to tell whether it has a solution or are just polynomials with positive coefficients, because we don't get a priori bound on the degree of polynomials in these solutions. So we might end up with infinitely many equations over n. And from now on, we'll illustrate this metabelian group using this specific group, Z2, and I'll write it in a matrix form. So just to highlight its connections with polynomials. So it's a matrix group, 2 by 2 matrices, upper triangular, where the upper right corner F is just a binomial or a binary polynomial over two variables. And these are Laurent polynomials. And on the upper left corner, we have a monomial with, of course, monomials of Laurent polynomials, and their exponents are over Z. And the multiplication is with group law, and the commutator of G, obviously, it's isomorphic to a polynomial ring, the additive group of this polynomial ring, and the abelianization of G is Z2, and this corresponds to the upper left, the exponents in the monomial in the upper left corner of G. Yeah, and again, as an example, let's take 3 elements, A1, A2, A3, and again, I already specified their image in the abelianization -2, 3, 2, 0, and 0, -2 in the exponents. And we want to decide whether there exists a word over these 3 letters, such that product is the identity, and you also want to use all 3 letters, but that's obvious. And I didn't specify F1, F2, F3 because it will depend on these 3 polynomials. The answer will depend on these 3 polynomials. Every word corresponds to a path in the Cayley graph of Z squared, and you can project this Cayley graph to Z2 by just considering the abelianization, so the exponent on the upper left corner. So in order to get a cycle in the original Cayley graph, you would, of course, want to cycle in the projection as well. So let's start with a cycle in the projection. Let's say with this word, then we consider the Cayley, so the path in the Cayley graph corresponding to this word projected on Z2. We start with A1. Its image is -2, 3. So we get this, and then we get A2. Its image is 2, 0, and we get continue this path, and then we just read each word, and in the end, indeed, we get a cycle, but this cycle is in the projection on Z2. It's not necessarily a cycle in the full Cayley graph of this read product. So this shows that, well, cycles in Z2 correspond to path in the original Cayley graph, and also correspond to words whose product has 1 on the upper left corner. But it's not clear how we can get a 0 on the upper right corner, which is what we want. To put it in another way, this cycle in the projection does not necessarily lift up to a cycle in the Cayley graph of the full group. So we want to find a condition such that this cycle in the projection can be lifted up to a cycle in the Cayley graph. And therefore we want to find this condition. And in fact, to describe this condition, we need to use polynomials. So I will define what's called the position polynomial of this graph, this projected graph. Say, well, now we have a graph. I associate to it three polynomials, P1, P2, P3, where Pi is the sum of all monomials corresponding to the starting points of edges with label I. I'll illustrate it. So to define P1, we look at the edges with label 1, which correspond to words, letters, P1. So there are two of them. And their starting point is at 0, 0, and 2, minus 1. So they correspond to the monomials 1, which is here, and x1 squared, x2 minus 1, which is here. So P1 is defined as adding up these two monomials. And similarly, to define P2, there are two letters, A2, in the word, corresponding to two edges in the cycle, and they have two starting points, minus 2, 3, corresponding to this monomial, x1 to the power minus 2, x to the power 3, and 0, 3, which is this polynomial. And similarly, we can define P3. And it turns out that there's a very simple description of whether this cycle in Z2 lifts up to a cycle in the full kilograph. That's just a linear equation over P1, P2, P3. It's actually quite intuitive because it's, well, okay, I'll not get into details, but let's say, well, it can be fully described using this homogeneous linear equation, where the F1, F2, F3s are the entries in A1, A2, A3, the matrix entries. So we have a word, W. We say that the upper left corner in the product of this word is 1 if and only if its corresponding cycle, its corresponding path is a cycle in Z2. We also showed that this cycle can be lifted up to a cycle with full kilograph if its associated polynomials satisfy a linear equation. And do recall that by the definition of these polynomials, these polynomials are defined by adding up monomials. So they can only have positive coefficients. It would not make sense to have minus something here. So we have this hidden condition that the coefficients of these polynomials are positive, and they satisfy this linear equation. So now we are in a better position. We have a mixed condition of a graph theory description and a linear equation over these polynomials associated with this graph. We want to combine it. We want to describe this property of being a cycle using these position polynomials. So can we do it? Well, if we think about it, a cycle is just a graph that's connected and such that at each vertex, the in degree is equal to the out degree. And the second property, so the first here, at each vertex, the in degree is equal to the out degree, can be easily described using these position polynomials. It's just this, because recall that P1, for example, is just the sum of all monomials corresponding to the output, so the origins of the edges. And if we add them up, this would just correspond to the sum of all monomials of the origins of edges. And if we look at the left-hand side, for example, this corresponds to the sum of all monomials corresponding to the destination of edges. P1 is the sum of all monomials corresponding to the start of edges. By multiplying this monomial, we are actually translating it to their destination. And by adding this up, the left-hand side is equivalent to the sum of all monomials corresponding to the ingoing edges. And since they are equal, they must satisfy this linear equation. and it's an if and only if. Connectedness is much more difficult to characterize. So let's just say it's characterized by some degree conditions that I'll specify in the next slide. So the problem of characterizing connectivity is that its global property depends on the whole graph. But these position polynomials, recall their definition, they're just sums of polynomials. They're just sums of these vertices appearing in the graph, and so they are describing only local properties of the graph. So there's no good way of describing them. Now the idea is to introduce a new property, which I call phase accessibility, that's local, but that's also related to connectivity. So I say a graph G is called phase accessible if, so let's see the convex hull of all the vertices of this graph, gamma, and gamma is called phase accessible if for every strict face of its convex hull, gamma contains an edge leaving this strict face. So let's look at, for example, the graph on the left is phase accessible because if we take any strict face of the convex hull, the convex hull here is the gray area. For example, if we take this edge, this strict face here, well, there's this diagonal edge leaving this face. For example, if you look at the bottom face here, then indeed there's this vertical edge leaving this bottom face. So if we take any strict face, there's an edge leaving. Whereas if we look at this graph here, well, we take this strict face on the right. Oh, there's no edge leaving this face. So it's an isolated kind of not accessible face here. And now I want to describe phase accessibility using the degree of these position polynomials. What's the degree? I will just, so the degree of a monomial, okay. First we have a vector, take any vector in R2, we define the degree weighted at direction V to be this max. For example, the degree of a monomial is just the dot product of V with the exponent vector of this monomial. And to define the degree of a polynomial, we take the maximum of the degree of all its monomials. That's it. Example, if we look at direction 2, 3, then the degree weighted at direction 2, 3 of this polynomial would be the maximum of the degree of x1, x2, and x1 squared. The degree of x1, x2 is just 2 times 1 plus 3 times 1, which is 5. Degree of x1 squared weighted at 2, 3 is 2 times 2 plus 3 times 0, so it's 4. Take the maximum, it's 5. So the degree of this polynomial is, well, weighted at direction 2, 3 is 5. And it should not be surprising that the phase accessibility of a graph can be described by a sentence in the first order theory of degree of PI, where the weight is a variable. So I can even give this sentence, but it doesn't make much sense. So why is it true? Because if you think about it, phase accessibility only depends on the behavior of the graph at its extremities, at its straight faces. What happens in the middle doesn't matter, as opposed to connectivity. And what describes these degrees? They describe these, the degree at some direction describes the behavior of this polynomial at the extremity of this specific direction. So by quantifying over all directions, we're actually describing the monomials of this polynomial at all the extremities. So then the degree of a polynomial actually describes the behavior of this graph at its extremities. And if we can describe the behavior at all these extremities, then we can describe the phase accessibility. And writing this sentence is just a matter of translating this sentence into a description using these degrees. Yeah, so let's say we can describe phase accessibility using degrees of position polynomials. So next would be to connect it with connectivity, because, well, the goal is to give a characterization of connectivity. So we have the following proposition. I'll use an example to illustrate it later. Let gamma be a symmetric, meaning, well, symmetric graph is just a graph where at each point in degree equals to out degree. Let gamma be a symmetric and phase accessible graph. Then there exists a finitely many vector such that the union of translation of this graph under these vectors is connected. So, and since gamma is symmetric, it's also a cycle connected, well, symmetrical. What does it mean? It means if we take some phase accessible graph here, for example, we can translate this graph. For example, we can get a red copy of it, translate it to the right for one step, and take the union of these two graphs and get a new graph. We can take another copy of it, another translation of it, the red, the orange copy here, add it into the graph, and finally we can take a fourth copy of it, a fourth translation of it, the purple one, and we take these four translations, interpole them together, and we get a connected graph. So basically, the proposition says you can always find these finitely many translations so that together they become connected. Now it might seem obvious. But actually it's not true for non-phase accessible graphs. Because if we take this non-phase accessible graph, this phase is not accessible, then no matter how we translate it and put these translated graphs together, it can never be connected because it will always have an isolated at this non-accessible direction. Yeah, so we're done. Almost. So how do we solve the group problem? So is this semigroup a group? So first of all, a semigroup generated by S is a group if and only if there exists a word over the alphabet S that contains every letter such that the product is the identity. Easy. Then we use this cycle description saying, well, that happens if and only if there's a cycle in the Cayley graph, and if we project it onto Z2, means there's a cycle in Z2 whose position polynomials satisfy this linear equation, meaning it can be lifted into the cycle in the full Cayley graph. And then we replace cycle with a connected graph who's symmetric, and we can describe symmetric with another linear equation. And then we replace connectedness with phase accessibility. And since if a phase accessible graph has position polynomials satisfying these linear equations, we can find a union of translation of it that's connected, but also the new position polynomials, the position polynomials of this union of translations, is obtained by simultaneously multiplying a single polynomial to P1, P2, P3. And since these polynomials equations, these linear equations are homogeneous, simultaneously multiplying P1, P2, P3 to a polynomial doesn't change the fact that these two linear equations are satisfied. So there's no problem. And finally, phase accessibility can be described using these degree conditions. So this first order sentence we talked about, and finally it's completely reduced to solving a system of homogeneous linear equations over the semi-ring of polynomials with positive coefficients, plus this degree condition. How do we do this? It's still non-trivial, I'd say. You're given a system of linear equations and you want to decide whether it has a solution with only positive coefficients. Let's look at this example. We have a single equation. Does it have a solution over n of x1, x2? Yeah, you also can't enumerate it. There's no algorithm that decides it because you can't enumerate all polynomials. There are infinitely many of them. And for this specific equation, I can tell you no, there's no solution because there's this trick. You evaluate this equation at x1 equals 3, x2 equals 2. Well, then what does this equation become? It becomes, well, x1 minus x2 becomes 1. The second coefficient becomes 1. Third coefficient becomes 2. And then it becomes an equation over n. But because P1, P2, P3 have positive coefficients, when evaluated at 3, 2, they're still positive, right? Then we have a positive linear combination of positive numbers that cannot be 0. So, the original equation cannot have a solution with positive coefficients. Yeah, but that's just a special case. If we look at another case, the same trick doesn't work. If you still evaluate at 3, 2, yeah, and this would be -1, so it doesn't work. Now we need to find a new proof. The proof is to, again, an evaluation. To evaluate x2 at 2x1 and let x1 tend to infinity. You can, well, then these three coefficients will still be positive. Well, if they make sense, they're at infinity, but they're positive. So this is still a certificate that this linear equation doesn't have a solution with only positive coefficients. And in general, it turns out that we can prove this local global principle that says if a linear equation does not have solution with only positive coefficients, then we can always find such a proof, such a certificate. And that's expressed using this theorem. So let M be a submodule of z of x to the power k. So x can be a set of variables, but essentially M is just the module of solutions of a linear equation. Then M contains an element with only positive coefficients if and only if these two conditions are satisfied. Essentially, the first condition says there's no certificate of the first kind, and the second condition says there's no certificate of the second kind. And I will not give the proof of this, but I can give a big proof of this. So what's the main idea in this proof? It's called pure states. So let A be a commutative ring. Let A plus be a sub-semi-ring of A containing 1. A state of A is just an additive group homomorphism from A to real numbers, such that the image of A plus is positive, is in the positive part of the real number. The set of states, so a state is just additive group homomorphism. It doesn't care about the multiplicative structure of the ring A. The set of states of A form a convex set. Obviously, if we take the average of two states, it's still a state. Oh yeah, 1 has to map to 1. The extremal point of this convex set of states is called pure states. So these are states that cannot be written as an average of two other states. And well, it's quite obvious, an element in A is an A plus, if and only if its image is positive under all states. So if and only if its image is positive under all pure states. And note that until now, we didn't use the multiplicative structure of A at all. But what's interesting is that Engelmann proved that under this condition for the ring A, then the pure states of A are actually ring homomorphic. So they preserve the multiplicative structure of the ring A. So what's this condition? It says for every element of A, there is a natural number in A, such that n minus f is in A plus. So it's almost like an Archimedean condition on the ring A. We're saying A plus cannot be too small in A. Right? It has to be dominated by natural numbers in A. And this is super important because it somehow magically makes the multiplicative relation appears in A. And if you think about it, if elements of A are just rational functions, then the pure states of A are ring homomorphisms, but it's from A to R. So essentially they correspond to evaluations of these rational functions at reals, or taking leading terms, meaning that you can evaluate the rational function at infinity. So this is already quite similar to what we wanted to prove. So indeed, that's the main idea of proving this local global principle. So we have a global part saying, well, a submodule of z of x to the power k has an element that has only positive coefficients. And we have a local part that says, okay, at every evaluation, this module contains a positive coefficient. So this is some abstract nonsense, but the global statement would correspond to a cleverly constructed ring A of rational functions and a cleverly constructed sub-semi-ring of A. And the local statements here would correspond to the pure states of A, because we call that pure states are ring homomorphisms, so they correspond to evaluations of rational functions. Now, the whole difficulty is construct this A, which is highly non-trivial. So I will not give this construction. It will never finish. Yeah, don't forget we need degree constraints because degree conditions, because we need them for the connectivity of the cycle. And somehow magically, you can generalize Einsiedler's theorem by just adding degree conditions in the global part and some modified local version of the degree condition in the local part and still make it work. If this is maybe a coincidence, but it still works. Yeah, and finally, what about decidability? We want to decide whether a system of linear equations has solution over polynomials with positive coefficients. And we have this local global principle. So for deciding it, we just need a double procedure. The first, we run two procedures simultaneously. The first procedure just enumerates all elements of the solution module M and check if it has only positive coefficients. And the second procedure enumerates these pure states. So in theory, there are uncountably many pure states, but you can actually show that it suffices to consider a countable subset of them. So you enumerate these pure states, and because of local global principle, one of these procedures must stop. And if the first procedure stopped, then you found an element with only positive coefficients, and if the second procedure stops, then you find a certificate that says, oh, that linear equation doesn't have a solution. So we get decidability, and in the end, translating it back to the metabelian group, we get that the group problem, deciding whether a semigroup is group, and the identity problem, deciding whether the semigroup contains a neutral element, are decidable in finitely generated metabelian groups. Okay, we only proved it for Z3 Z squared, but the same strategy can be done for all finitely generated metabelian groups. Yeah, that's it.
Thank you very much. Questions or comments?
Thank you for your talk. Can you find any estimates for the length of this algorithm?
No. So I suspect if you work really you can actually prove. I think if you work really hard, you can prove quantitative version of this local global principle. If that's true, that's only my conjecture. Then you get a tower of exponentials in complexity. So, so it's not practical.
Thank you. So, and you don't know any interesting examples when the minimal length is huge?
I don't know. I haven't tried. Yeah, the problem here is you don't. So what I partially did is that instead of the double procedure, you can actually check finitely many pure states. That's not true, but that's almost true. In that case, maybe you don't need to find the length of this solution. You can just check pure states. But that didn't work out completely. There's some hope, still some hope to it. I'm not doing that actively.
I also have another question. The lemma you mentioned that finitely many translations from a connected graph. Is it also true in dimension 3?
Yeah, it's true in all that.
In any.
Yeah, but then the faces you consider you need to consider the faces of all dimensions. So if you have n-dimensional polytope, you have n-1 dimension faces, n-2 dimension faces, and 0 dimension faces. So that's true. Yes, that's still true.
For three steps of groups.
Well, the word problem is on this side.
Yeah, that's
Yeah, so yeah, good question. Actually,
I mean, is it directly implied like that, or
no.
but is there another applications? Because I was
Yeah,
thinking that, but I didn't know.
Yeah, so if we take just the semigroup generated by one element and asking if the semigroup contains the neutral element is just asking whether this element is quotient. I think the whole thing. It's not the same as word problem, but it's probably you can put on the time.
You expect that you can find an example where it's decidable.
Yes, but one interesting possible future work is, well, here we're considering actually a direct product of two abelian groups, right? It's a direct product of what? Oh, that's fine.
Semi-direct, you mean?
Yeah. Well, we're considering a direct product of this map.
Semi-direct, yes.
Semi-direct. Yeah, sorry. Semi-direct. Yes. So the idea is maybe if we replace the abelian group A with a two-step nilpotent group, then there is still some hope of solving. But this would imply you need to generalize these pure state stuff to a non-commutative ring. Yeah, then becomes quite challenging.
I had another question or remark, which is that in fact these polynomials P1, P2, P3 that you wrote, they really are, saying it pedantically, the Fox derivatives of the word. Okay. So there's big theory about words in a free group that essentially you take the prefixes and you multiply. Fox derivatives. Take then it's a linear combination of words, and then you evaluate it in a representation, like for example, taking these polynomials. So there could be something quite general for all groups that map onto Z to the K with a nice enough kernel, where again, you would use something a little bit more general than this. So the first example that comes to mind is finitely supported permutations extended by translations. So every permutation of points on the plane that outside of a finite region act as a translation, always the same. That's a nice finitely generated group.
Okay.
And what is the question, Laurent? Whether also these problems are decidable in this group, or?
And whether a variant of the algorithm would work, which now has to combine some amount of linear algebra and some calculations in a locally finite group, as opposed to the a positive polynomial problem. It would reuse the first part. All the graph theory and so on will be reused. But then the final solution, we cannot use the Einsiedler positive Stellensatz criterion. But we'll have to use something more combinatorial. Yeah, these are interesting groups.
Yeah.
I mean, for this group, it's kind of trivial because you just need to look if you can come back to the origin and then its torsion. So.
Oh, sorry, the audio does not come through.
Oh, okay.
Yeah, you say that it's not an interesting question. Too bad. I'm sorry, but you just come through as 50 hertz.
Morse code or something.
Or Morse code, yes. Oh, Arié has, or maybe it's my computer actually that's. Hello, Arié. Unfortunately, we cannot get any audio from. Yes, can you please type your questions in chat and then I will read them out loud.
May I ask meanwhile some other questions, Laurent?
Yes, please do.
So I have several questions. So your results about metabelian groups, right?
Yes.
And what happens for solvable group? Take a solvable group, let's say this, suppose that your problem is decidable, maybe. What happens then more generally for solvable groups, or what is expected?
Good question. This would probably, so as I said, it would at least imply we need to solve the problem in the direct product, semi-direct product of a nilpotent group and a module over this and a group ring of this nilpotent group. And that would imply generalizing these pure states in commutative rings, and that seems really challenging. So I don't know what will happen for a group with decidable word problem.
But you admit the ability that maybe for a much larger class of solvable groups, there could be some generalization of your result, or what?
Yes, I think so. I think maybe in what's it called, abelian by two-step nilpotent groups. Maybe that would be a reasonable class to consider.
So Corentin interjects that even for unsolvable word problem, it's non-trivial. So the result that the identity problem is non-decidable in SL4Z is pretty recent.
Yes.
Yeah, so.
And my other question is about membership problem in semigroups. I understood that for metabelian groups, there were some counterexamples, right? For nilpotent groups, some result of Romankovsky, right?
Yes.
And I understand you also had the result about Reef product that for Z with Z it's not decidable.
That's not.
Or it's not result.
That semi-group membership in Z with Z is undecidable, right?
And whose result is that?
Marcus Lori, Georg Zetscher,
Maybe Armin Weiss also.
not him, but one more guy.
And is there some understanding what happens in general for this problem for metabelian groups? Can one have a characterization or something of metabelian groups where it's not decided?
But maybe it's not correct. I think it may be decided, so semigroup membership may be decidable in all lamplighter groups. So Rees product of free metabelian, so Rees product of a finite metabelian group and Z to the power n. So high dimension.
You the finite group, maybe it's decidable. So in Z it's not decidable. If there is some group containing Z with Z as a subgroup, would it be undecidable?
I think so. In these, so that there's two restrictions. There's this restriction on the second Z, and there's also this non-torsion of the first group. So what I guess is if you say, well, in the Rees product, the first group is torsion or finite abelian, then maybe you can always get decidability. Not
Or
sure.
really, even if it's not one-dimensional, for example, for two-dimensional Rees product, what happens? You take two-dimensional lamplighter. Do you think it's decidable?
F2 Rees Z squared has decidable semigroup membership. But F2 Rees Z to the power 3 is open. Yeah, that's but I suspect it may still be decidable. So if we restrict the first group in the Rees product, then maybe we can get a lot of freedom for the second group. And similarly, if we restrict the second group in the Rees product to Z, for example, then we may get a small amount of freedom in the first group. But as you see, Z with Z is already dead, so not so much freedom. But if we say, well, what about? Yeah, I guess that covers most cases. There's really this torsion that this torsion in the polynomial ring and torsion in the Rees product that matters. Not in the Rees product, but in the first group of the Rees product.
Very good.
Thank
Other
you.
remarks? Or- yes. Oh, Anna had one more.
My last question, yes. So I wonder whether some of these algorithmic problems, whether there is some relation with the theory of rich groups of Harlampovich and Мясников, because some metabelian groups, right, like free metabelian group, but also Rees products that I'm not sure, I think also are known to be rich, meaning first order, if there is some other group with the first order theory as in this group, then it's equal to this group, right? And in such rich groups, if I understand, if you have some submonoid, it's always definable. So so there is something a bit related maybe to question about semigroups. I wonder if the algorithmic questions you discuss might have some relation.
I have no idea.
Okay.
I don't know about Мясников's results
Harlampovich.
and how.
Yes, lots of other things to look at.
Yeah, so correct. I need to decide that. So the semigroup membership is divided. But when I say F2, I really mean the finite group. Semigroup membership is decidable here, but it's open here.
Yeah.
The screen is very dark, so now maybe better.
Yes. Now it's more readable.
That's it. I'm like this, right?
Yeah.
The state dimension.
Yes. So as you see, it's really weird situation.
for now.
Yes.
Okay, thank you very much, Ruiwen.